All right. Hello, everyone. Welcome to another episode of Quirkcast. This is your host, Tim.
I'm Mikey.
This is Sahil. Welcome everybody to a brand new exciting episode of Quirkcast. If you haven't already, do join our Discord channel so you can ask us questions there. Also, if you're listening to this on YouTube, post any questions that you have and we'll get to them during the episode. And then last thing is, if you listen to this on a podcast, Apple, Spotify, or wherever you get your podcast, do rate and review. That's incredibly helpful to us to make the show better for you. So without further ado, I guess Tim, I was cooking a dish the other day, and I was thinking, like, I mix different ingredients together and heat things up enough and then let them cool down. Can the same analogy apply for creating a universe? Just like arranging a bunch of atoms together and things just happen?
Very specific about the warming up and cooling down thing.
I think that's a very apt. I think that's a very apt analogy. And when I was a student learning about cosmology, and it definitely seems like many of the terms are familiar. So especially if you buy the Big Bang, the theory of Big Bang, the universe used to be hot and then it cooled down. So it's almost literally like there was a kitchen somewhere, like a abstract kitchen, and stuff were cooked and in the canvas of a space and time, and then eventually we got our universe. So I think it's a fair question to ask, if that's how our universe came to be, like who are the chefs and kind of like what's the recipe?
Yeah. So I ask you guys, what is the recipe for the universe? Is that even answerable? What am I asking even the right question?
Yeah, we're always limited by the scope of like what human questions can capture, right? Like, so there's so many different ways to think about this. I think everyone could have their own opinions about what are, like, what kind of aspects of the universe were, key to it looking the way it is now, or even the way, what kind of features of it were crucial for it even being able to exist in its current form. And I don't know, I think we should have a debate about this. Tim, what do you think are the most important ingredients?
The most important ingredient,
plural.
The ingredients. Yeah. Well, I think it a bit depends on the kind of things that you emphasize on. Well, of course, like we're talking about our universe, not just any universe. So to humans, the most interesting things in our universe are stuff, right? Like galaxies, planets, and ultimately us. So I think it's fair to say that the important bits that we're interested in is what we call matter, or more generally, just some sort of energy. Without energy, there wouldn't be anything. And interestingly, the energy could be broken down into a few different types of energy. And these all have different characteristics. You can think of them as like different types of ingredient when you're baking the cosmic pie, right? And I think we can generally agree on these three types of energies: radiation, which is like X-rays, gamma rays, light. Basically, it's like you go to the doctor, you go to the radiologist. Yeah, that's the radiation.
Light. Let's keep it simple. I think there's lots of other kinds of radiation, but the kinds you mentioned, it's all light. It's all the same stuff. So there's
the radiation. Essentially. Yeah, so essentially that's a radiation. I think it's fair to say that's like the soup base of the universe. Is that fair? Kind of.
We're all swimming in a soup of radiation. I mean, especially now, like we're sending signals through cell phones and all these communication systems that are encoding our personal information in this soup. So it's like the soup is kind of sending off our private information.
Yeah.
Being aware is very important in this day and age.
And then of course there's the matter bits. These are like the stuff, I don't know, cups, tables, and laptops, and humans. We just lump them together, we call matter. But more intriguingly, matter actually includes another form called dark matter, which is not exactly the same as the matter we see every day, but it's just extra matter that you can't see or touch, but exists in the universe to help make this. Yeah, it's kind of like the chunky bits of the universe. I think that's fair, right? It's
Well,
like
we're
it's what. Oh, I guess we were extra chunky.
we're more similar to dark matter than we are not, right?
Yeah, I feel like in that regard, from a human perspective, I think us, the type of matter that we are, which can be called the baryonic matter, which is the common type of matter, is the most important one from a human perspective, right? I think, and then of course the rest is that there's also dark matter. It's a different type of, slightly different type of matter, behaves somewhat similarly. That also helps the chunky bit, but I think from a human perspective, the baryonic matter will be kind of the most important, because that really is what drives our existence. I don't know.
Tim said baryonic matter without defining what that means. You should scold him.
Also dark matter too.
Oh boy.
What is that in like a tiny nutshell? I know it's super expansive and people spend years studying this stuff, but is there a way we can condense that down into like one or two sentences?
Yeah, let me take a stab in terms of the kitchen, the food analogy. Dark matter is kind of like people liken it to like cosmic molasses, like a thick, stewy, kind of like
Wait,
like
that makes it
gravy.
sound very different though. Wait.
Because
If we're thinking about the three basic ingredients, right? Like you mentioned radiation. And what makes radiation radiation, right? It's the fact that it has, these are particles like light that have no mass. And so they're free streaming around the universe at the speed of light. And they basically are less like actual particles and they're more like the soup, as Tim was saying. And then you have the matter stuff, right? The stuff that's heavy and it clumps together because of gravity. And within this matter category, you have two different types, right? Ones that interact with the radiation, which like us, right? We interact with light, we use it to see. So we're very, 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 very much tied to the radiation. We're the very small minority of this clumpy matter that actually can communicate with light and can see light. But there's this other big part of this clumpy matter like component of the universe that has no access to communication with light, which means that we can't see it because we see things that light scatters off of. It means, in fact, like the fact that we can even touch things is dependent on the electromagnetic interactions between the surfaces, which is a form of light. So it means that we can't even like feel this form of matter called dark matter. It's literally like a ghost to us. It's one of the big puzzles of cosmology right now is we can see it, we can see its behavior, we can measure its properties, but it's just so hard to characterize exactly because it literally just passes through us, and that's what dark matter is.
What's the third ingredient?
We didn't get to that one yet.
yeah, that one is tricky. So I think so far it's almost like, I guess we kind of have like cosmic stew, right? How about this analogy, Mikey? Tell me.
It's not. It's kind of the simplest one, right?
Huh?
It's kind of the simplest one, right? The last ingredient. The last ingredient is literally nothingness, right? It's the energy of empty space.
It's the dark energy.
Yeah. So it turns out that even space and time. So if you take space and time and you take out all the stuff in it, all the matter, all the energy, you have completely empty space and time, right? Except no, it's not completely empty because space and time carries this kind of intrinsic energy with it. That if you double the amount of space, you double the amount of this energy in a very reliable way. And that intrinsic energy is the third component of the universe, right?
So I guess like how do you distinguish between like these, like why these three in particular? How did like, are they non-overlapping or why is it that particular segmentation of three?
That's a good question, right? That comes from the evolution of the universe, right? Like, so if you ask, what are the three things that the universe is like, big picture shape cares about the most? It's these three forms of energy.
Yeah, I guess the analogy is you have all the ingredients of this cosmic pie, and you put it in the oven, which is the universe, and you bake it for like 10 billion years plus. And during different times of this baking process, certain parts of the pie will do certain things. And this behavior of these different parts of the pie is essentially what dictates what distinguishes them, the different ingredients, right? And I think it's fair. I think I sort of like this analogy. It's almost like so the soupy stuff is sort of the radiation, right? It kind of gets baked into the pie, and eventually it does go away. It kind of evaporates out, becomes unimportant. But it's important to have the juiciness in the beginning, and then the chunky bits are kind of like us and dark matter. I guess us you can link it to the good tasty bits, like the flavorful bits. Dark matter is kind of like just like a filler. It's kind of like
okay, so you're describing a casserole. You start with a stew and it evaporates, yeah. And
is that right?
And then our matter is the meat, which is always too little of, and then dark matter is like potatoes, right?
It's the filler.
Potatoes. It just keeps everything together and gives you enough carbs to keep everything healthy.
Right. But what is dark energy? I think I struggle with this part.
Could you say it's the pot growing bigger, or not even the pot growing bigger? Just like the space of the pot is growing bigger. Like,
I guess, is it fair to say that dark energy doesn't matter very much until recently?
Okay, so maybe it's worth talking about why the universe cares about these three things the most. It's kind of an interesting fact that if you look at, so the universe is expanding, right? And given the fact that we don't know whether or not the universe has a physical boundary, the only way to track its expansion is just to track its expansion with two imaginary points, right? Point this way and point that way. How fast are they moving away from each other? And it turns out that if you look at the history of the universe, and this is confirmed by numerous astrophysical experiments and theoretical thought experiments, the universe has a birth time, and if you want to get the birth of the universe right, its evolution follows a very particular sequence of first, okay, I guess theoretically first blowing up, and then kind of like rounding out, and its expansion kind of slows down, and then it kind of blows up again, like right around now. So this is how the universe is expanding. It kind of blows up in the beginning, and then it kind of like teeters off and kind of rounds out. It slows down its expansion, and then as time goes on, it blows up again. And that's the future that we're looking at right now, a universe that's going to continue to blow up faster and faster and faster. And if you ask why the universe expansion is shaped in this way, it's because of the fact that at different parts of the universe, like very early on in the universe, most of the contents was radiation, massless particles. So the universe is expanding a certain way because it's responding to that energy. And then as galaxies form and particles form and things evolve and become clumpier, then the universe becomes mostly matter, and it kind of changes the way that it expands. But as it expands, the amount of matter is getting diluted, and it becomes less important. And so then it kind of blows up again under this new force, that is determined by the amount of empty space that exists.
so would one way of saying it being the early part of the universe was radiation dominated, then the middle part is matter dominated, now we're dark energy dominated?
Yes, those are the technical terms. Of course, you knew that. Good.
I vaguely pulled that from my memory.
Exactly.
I see. So then eventually, like, will none of the other two ingredients matter that much? Will just be only dark energy, and that's it. Like,
That's our cold.
Yeah. I guess that's like burning your pie. Like it's been in the oven long enough. It turns out that if you leave it on a very long time, the pie just kind of explode. It just blow up into nothingness. So right now, I think the pie is quite tasty at this moment.
Yeah, it's literally follows the trajectory of like a steak, right? Like you cook it and then there's like a sweet spot and then it just becomes less appetizing as time progresses after that. And it's like an interesting argument. Like people, from a cosmic perspective, our existence is a very small blip, right? But we happen to live at this kind of interesting time where the universe is just starting this transition, so things are still slightly present. But in the future, the universe will be so big that you won't even be able to see a star. So if we couldn't see any stars, how would we ever, figure out anything about astronomy or our place in the universe? So it's kind of sad to think of beings that live in the future.
I suppose since we're talking about the recipe, we haven't talked about the proportions yet. Should we go into that? That's a bit ambiguous, right? Actually.
Yeah. What do I need to do to create a universe?
Wait. So before we get into this, like I know the title is called "Recipes for Making Our Universe," right? But you can imagine lots of different universes. So if we're talking about the proportions, we're going to start talking about things that are specific to our universe. But if you believe in the multiverse as modern physics and the Marvel Cinematic Universe would like you to believe, then this is kind of a real concept, and it's based on real physical motivations. So let's talk about our universe. What makes our universe special that life can arise?
Yeah, well, I mean, one specific part is that we have some pretty interesting ratios, a mix of these ingredients, right? Radiation, matter, ordinary matter, dark matter, and dark energy. But I guess it's not as simple as comparing it to like a recipe book, because like a recipe book, you start with some ingredients and you chop them up and then you make something. But unfortunately for the universe, we don't have that, right? It's not like the
it's very analogous, because they're saying that do it this way if you want it to taste good, right? So we can say do it this way if you want people to live in it.
Right, but the amount of ingredients actually changes across time. So that's sort of the difficulty with this analogy.
No, but salt, water evaporates and salt density changes.
So there's a limit to how far we can go with the cooking analogy.
I don't think so. I think it's an exact analogy all the way.
Then I guess do you suspect there are other ingredients, or are those like 3 ones that we just know about?
Ingredients that we haven't seen yet?
I think when we say these 3 ingredients, we're not too picky about the specifics. Chances are any new extra ingredients that we might discover are just into one of these categories, right? It's almost like
no, he brings up a very interesting point, because like we're talking about the ingredients that we interact with, right? What are the ingredients that are fundamental to our existence that are necessary to give rise to humans to even think that question? But it's very real. And Tim, I think you even studied some of these things. But there could be completely random components of the universe that are completely disconnected from us. Like dark matter could be actually completely separated from our universe in almost every single way, and it could be very complicated, and there could be a lot of stuff hiding in there.
Right, but I guess the question is dark matter. Like it's almost like dark matter could be made of something else. It's almost like when you look at like a snack, you look at hey, ingredient is chocolate, but then there's parentheses, chocolate is also made of something else. So I guess that's quite plausible that dark matter is also made of some other ingredient, and I suppose we could discover them.
Yeah, well, I mean, Sahil was asking, like, are there parts of the ingredients of the universe that we don't know about yet? Right? We barely know about dark matter, right? Barely. Like, who knows? it's a proof of concept that there could be tons of other things that we don't know about at all, but are right next to us.
I suppose we mostly know about the proportions of them, like the total amount of mass and energy. And that's roughly the most important aspects of the cosmic pie baking.
Yeah, but those are things, I don't know, because those things are, could be related to anthropics, they make me very nervous, right? Like these, I guess, okay, so to explain what Tim's talking about is, if you look at the amount of dark matter versus regular matter in our universe, and if you look at the amount of dark energy in our universe, they're very specifically proportioned, like a baking recipe. You get the amount of sugar off by a little bit or flour off by a little bit, and the whole thing goes to hell. I don't know, that makes me a little nervous thinking about, right? Because we're talking about now things that are required for a universe that could give rise to us to ask those questions in the first place. So you get that kind of troubling recursion that gives rise to anthropic arguments, right?
Isn't it more that the anthropic argument is just simpler? And so we're here because we're here.
Yeah, I'm not a big fan of Occam's razor. Are you? I don't know. Things are as simple as they have to be, and not more. But humans always wish things would be simpler than they actually were. So I think Occam's razor comes with bias, confirmation bias effect.
What about more of the limitations of I guess the language of physics as well, of being able to capture things that are countable, but
I don't know if I would say that physics has any limitations of language, because I mean, if they're not limitations of, I mean, they are literally limitations of language, right? There's a limitation of physics. It's a limitation of our ability to either conceive of these concepts or to express them in a structured way.
Yeah, I think physics is, at least compared to math, is less limited. It's almost like we're trying to build something that's has as few limits as possible, because in physics we don't care so much about formality or proofs or mathematical rigor, as long as it somehow gives an enticing description that fits what we observe.
Yeah, so I guess if it works, it will be included. The limitations come from the fact that we haven't found anything that works to be included.
I think it goes back to your earlier point that if you can't measure it, does it exist? And so there's certain things that we can't measure. We just have no interaction with us, then might as well not exist, right?
Yeah, so I guess this episode is secretly rooted in the question of what it takes for our universe to exist, even as much as I'd like to believe that it's a question about general universes.
Yeah, I guess also saying that something is the most important, because you need all three of those things for our universe to be there. If any one of them is missing, as by a little bit, we'll get a completely different universe. Is that fair to say?
I think it depends. If it's like a tiny bit off, it might be okay. At the end of the day, the baking is done by gravity, and gravity dictates sort of structure of the cosmic pie that's being baked. So it's true that if you have, like, for example, if you have too much dark matter, it might get a little too chunky, and your pie might just collapse onto itself, and that's not very good. It wouldn't make a very enticing pie. Or if there's too little, that it wouldn't be chunky enough, then it would just be not such a tasty pie. It would just, maybe you just like, it would just turn into mush, right? So there is definitely this Goldilocks ratio that we have in our universe. I think it's what it's 75% dark energy, like 25 or 20% dark matter and 5% matter. But yeah, but that's right now. but this ratio changes as you go back and forth in time. So I think that's fair. I think that's right now, right? These are the numbers right now. But if you go back in time earlier, it can easily change.
Yeah, but I mean, their starting ratio determines their current ratio, so you can think of them as the same, though, right? Believe general relativity and
sort of. But but the way you notice that we didn't talk anything about radiation. Radiation is negligible right now.
Yeah.
But early in the universe, things tend to be radiation. I mean, actually, some of the radiation turn into cold matter. It's possible they cool down, and one ingredient can kind of turn into another. Although for some of the ingredients like dark matter and dark energy, it's hard to imagine they can turn into one another. That's probably not going to happen. So,
I see. Is it fair to say, actually, what is the primary source of radiation in the universe? Is it the cosmic microwave background, or is it something else?
Well, Tim said there's very little radiation in the universe right now, so you can think about it like when the Big Bang happened, it was kind of like an explosion of radiation, right? So that's why like the initial periods of the universe were very much radiation dominated. Oh shoot, can't remember how the story goes right now, but oh yeah, so as the universe expands, it turns out that radiation dilutes at a faster pace than clumpy matter. And we shouldn't get into the reasons right now. It has to do with the fact that radiation has a more wave-like characteristic. And so as you stretch the space, it loses not just, it loses energy, whereas like massive particles, right? There's a certain amount of energy that they can't lose. They can't lose more energy than what is equivalent to their mass. They hold that with them permanently. But, you know, particles like light, they can get arbitrarily low energy. So as the universe stretches, you basically stretch them out into non-existence. So the radiation is kind of diluting at a very fast rate as the universe is expanding, whereas the clumpy matter is not. So you can think about like in the beginning of the Big Bang, it released a ton of radiation. The universe is all radiation and a little bit of matter. But as the universe expands, the radiation dilutes super quickly until you basically just have matter left. And then as the universe expands further, the matter dilutes until you just have this dark energy left that we've been talking about, the energy of empty space.
And dark energy does not dilute.
Yeah, because it's intrinsic to the space. If you double the space, you get more dark energy. If you double the space, the matter volume goes down by cubic power.
So you're telling me like I can't just keep consuming mass and hope to like dominate, and there's no way, like accruing resources and like making myself larger and larger.
Does that mean that?
And that's fair. Dark energy will eventually take over everything. Like no matter how advanced our civilizations get, you will never escape the cold, icy grip of dark energy domination.
Yeah. As long as it's expanding, there's nothing to do.
Yeah.
Well, I'd rather embrace that now than later at the far infinite future when it takes over. So, well, we're almost, actually we're basically at time, and so I want to anything you guys want to say before we head out.
Yeah, I think it's nice because we didn't really get to talk about this, but we're talking about like different ingredients, right? And if you're describing ingredients for like a dish, you could describe it in different levels of abstraction, right? Like what's in a cake, right? Oh, it's just flour, butter, and sugar. But then if you get into like fancy cakes, what kinds of butter are there? Does it help to have certain portions with certain types of butter, others? And so we were sort of talking about that finer distinction right now. Like all of these things, matter, radiation, dark energy, they're actually all made from the same stuff, right? Like energy. So if energy is the thing that links all of these different ingredients that we were talking about, then there's really just space, time, and energy. So I think those are like if you really wanted to get to like what are the most basic fundamental ingredients that are required for making a universe, it's space-time energy with a little bit of artistry.
I suppose to echo that, to some extent, it's kind of surprising how us human beings can actually use such a simplified language to describe the grand structure of our cosmos. And believe it or not, it's surprisingly accurate and testable and scientific. And this is something that shocked me as well when I was a student. And like, I can imagine, surely the universe should be described by more than just a handful of numbers, right? The largest structure of the universe. But it turns out, no, literally that's enough, right? But like Mikey was saying, for the most basic overall structure of like what it takes to make a universe, yeah, it's quite simple. It's just space, time, and energy. Kind of like energy is just, you can go into finer details. Do you want the gourmet type of energy, the dark energy, dark matter, ordinary matter, radiation, right? Or you can go into even finer detail, which type of radiation, which type of ordinary matter, which type of dark matter, blah blah blah, right? But yeah, but I think also coming back to this idea that everything ultimately is energy, and at the end of the day, it's quite plausible that none of these distinction matters, right? Dark energy, dark matter, radiation, they could ultimately be one and the same thing. If we believe that the universe comes from a unified framework of physics. So I guess to some extent, or maybe even space, time, and energy are one and the same. And at the end of the day, the universe is just, I don't know, it's just a soup of itself almost.
So meta.
Wow. Well, on that note, I'd like to thank everybody for joining us, and we'll see you all next week.
Yeah, see you all next week. Bye.
Bye.